Sounds good.
All right, let's get moving here. I'll get started with today's CAN seminar. And we're lucky today to have Dr. Waterbrink, who actually about 2 years ago almost graduated from Michigan State University, who worked with Dr. Bush over there, Niraj Bush. Some of you may know. And the way that he worked on some pavement ME calibration studies, apparently, for Michigan. He was then hired there by ARA and came here to work in Champaign. Of course, Champaign has the best companies in pavement engineering. So one thing interesting about this presentation is actually on the use of the integrated climatic model that was developed over the years with the efforts from Professor Barry Dempsey here, as well as Greg Larson working with them. And now, as you know, that's a main component, climate component of the pavement ME design procedure. So Wouter will talk to us about evaluation of software simulation of road weather information system, which was actually something that was discussed also yesterday in a webinar by TRB that had running damage potentials of roads under spring thaw conditions. So with that, I would like to let Wouter to start.
Thank you.
Yeah.
All right, welcome everybody. Why are you all sitting so far away? I mean, there's so much room. I mean, I understand. All right, welcome. And my name is Waterbrink, and I'm a staff civil engineer with ARA. I started in 2015, as Harold just said. Most of my work is with Pavement ME, mostly calibration, a few other aspects for updating the software, implementing new techniques, and then some of my other projects I work. This is one of the fun ones I worked on, is comparing the actual road weather information system and creating a virtual site that can basically supplement those actual in-service RWIS stations. So that's my topic of today, and I'll go through that with you. So first, I'd like to just give you a brief introduction on what the EICM is, what we did for the study, and then I'll go over some of the data collection efforts, because we had to collect quite a few things to create these virtual road weather stations. And I'll summarize and discuss some of the interesting results that we found, and I'll conclude the presentation with our findings, and then also I'll go through a brief software demonstration. That way you can kind of see how all of this fits together. It's a pretty neat website that can really help winter maintenance crews and a few other things that what you want to do. So the first thing I want to go through is just how has pavement climate been modeled and how it's been developed over the years. So as you can see here, it started in the late 60s. Most of this research was done here at University of Illinois. And as we go through up until 98, the model hasn't really changed much since. I mean, some minor tweaks here and there to make sure that it can work with Pavement ME and predict your pavement temperatures and with depth. So basically, the EICM, Enhanced Integrated Climatic Model, is a heat transfer model that simulates changes in pavement and subgrade properties. So it uses rainfall, solar radiation, cloud cover, wind speed, air temperature, and at the pavement surface, and then it predicts pavement temperature, resilient modulus, adjustment factors, pore water pressure, water content, frost and thaw depths, and frost heave throughout the complete pavement and subgrade profile for its entire design life. So if you're familiar with Pavement ME, you can basically design a pavement up until 100 years, 50 or 100 years if you want, but it'll use hourly climatic data to predict these different material properties. And the main three components of the model itself is the climate material structural model. It has the frost heave and settlement model and the infiltration drainage model. And today, the main purpose will be to show how we use the EICM and characterize a pavement structure and get pavement temperatures to predict icing and freeze-thaw depths. So as you can see here, we have pavement structure, and we use the hourly climate data that comes with the Pavement ME software, which consists of temperature, percent sunshine, wind speed, and precipitation, and relative humidity. And we use those to run the EICM and get predictions to compare to the actual road weather information systems. And then we can determine how accurate those models are. So that's the main focus of this, is to really show you how well those compare. And what's nice about it is, with the current computing power, we're able to run thousands and thousands of EICMs to get those pavement temperatures, so we can provide them to you in real time. So, and we also have a way to predict it out up to 7 days right now. So it's a really, really useful tool to use. All right, so this is kind of a screenshot of some of the software. It was developed to show surface temperature and air temperature in real time for wherever you set up these stations. And it can also show you the historical data. So if you want to go back to 1994, if it was a cold weather spell in that time, you can see what actually happened. I'll go into more detail about this when we do the software demonstration. And then the second figure over here, you can see the blue is the pavement temperatures. Now if you sat closer, you'd be able to see this. So the blue lines are the pavement temperature, and the black lines here are the air temperature. So you can see as the days go on, so this is in November 2014, and then it gives you your 7-day prediction. So here you're not going to get, so your pavement temperature is above freezing, so you're probably not going to have any issues with ice. Now, once you get to this point where you can see your pavement temperature drop, same with your air temperature, now this red box basically show you the potential for icing. But it's also because there's some precipitation predicted for that area. So that's some of the benefits of the EICM, that it predicts the pavement temperature, so you can monitor when it's going to be close to your air temperature versus your pavement temperature. And when that temperature basically coincides, that's when you have potential for icing below, of course, below 32 degrees. And then the other aspect is, because the ICM gives you pavement or temperatures with depth, you can determine, you can see where your how deep your frost is and when your thawing starts. So it'll tell you here, the red's it's basically your thaw depth, and then you have your frost depth. So this is a fluctuation over time, and it can predict this fairly well. So I'll show you another chart that's actually part of this when we do the demonstration a little later. All right, so some of the objectives of the study, I kind of mentioned it already, is to basically determine the capabilities of the virtual road weather information system and compare the predicted and measured temperatures. And also, can we improve these models by changing a few parameters of the materials? So first I'll go into some of the data collection efforts in order to create these virtual stations for a particular location. So first we needed to collect all the actual road weather information system data. So they are scattered throughout the state. We looked at different agencies. So we worked with the Illinois Tollway, McHenry County, and Illinois Department of Transportation to look at all of their RWIS stations across the state. So their Illinois Tollway has 17 sites, only 13 with pavement sensors. McHenry County has 6, all of them have sensors, and IDOT has 58, and 49 of them have pavement sensors. So the thing about RWIS, these stations are very expensive, so they can't place them everywhere where they want them. So it's a very expensive system to install and to maintain. So every year there's a cost to it. And one thing that could be used with these virtual stations is supplement that data. And I'll kind of show you when we how it looks for how many virtual stations we created for Illinois. And the main data we wanted to look for was the pavement surface temperature and the cross-section information. So those are the main things we wanted to collect. So here's kind of an example of some of the data that you'll see from these RWIS stations. So these are the actual in-field. So this is something you want to, this is a good example because you want continuous data throughout a long stretch of time. And a lot of these stations had some missing data, so it just stops randomly or something will happen with the sensors. So that's the one thing. And we wanted to focus on temperatures between November and March because that's when you're typically going to see your pavement temperatures dip closer to freezing. And we also wanted to eliminate any bad or unrealistic data. Some of the values are, I mean, some greater than 140 degrees. I mean, that seems probably a little on the unrealistic side, especially for during colder temperatures too. So these are some other things to look at. So I kind of want to show you a few examples. But I'll show you those in a little bit. First, now we wanted to collect, our final site selection, we have to consider, basically we wanted to cover the entire state. So that was the big thing. So we're not just biased with the northern part of the state or the southern part. And we also wanted to make sure we cover most pavement types because concrete and asphalt responds differently to climatic effects. And then also we wanted to have thick or thin pavements because that also has an effect. So the final sites, we had 25 Illinois DOT sites. We had 9 tollway and 2 McHenry County sites. So here we see, basically it's reiterating what I just said. Just shows you a geographic distribution of where these sites are located and based on pavement type. As you can see, it's fairly well distributed with, I mean, all the tollway sites, of course, going to be up here near Chicago. The 2 McHenry sites are right here. And then the rest are mostly on interstate roadways, some smaller, lower tier roads. But it's a fairly good representation. All right, so the next data collection effort was to collect pavement cores to determine the different thicknesses for each layer. And we also did some look through historical records to find the base thickness and base layer type. And we also measured the pavement surface color. So these are the main physical aspects that we had to collect at each site. So the next thing we need to do, once we have all that information, we needed to characterize for each of the actual road weather information systems, we had to characterize a virtual station. So we wanted to be as accurate as possible, and we used all of that collected data to create an input file to an EICM to be able to represent that particular road weather information station. Once we have that, then we can run the software or run the EICM and get our pavement temperatures. So as you can see here, this is basically where we created all of these different virtual stations to represent what I just showed you in the previous slide for all the physical stations. And most of the RWIS temperature data range from 2009 to 2015, depending on the site itself. All right, so now we'll go into a little bit more of the data analysis portion, where we looked at how we compared the results. And the first thing, there was a lot of data processing to be done. I'm sure you've all experienced it where you get measured data and it doesn't really fit correctly right away. So we had to not manipulate, but we had to adjust a few things. So The measured pavement temperatures were in either between 5 and 10-minute increments, and our hourly climate files were on the top of every hour. So we had to do quite a few things to make sure that we compare the correct information. There was also some data error processing, so in the measured data, some sensor or some measurements were like 624 degrees, which is very unrealistic, so we had to take those out. We also had to run the EICM for all these sections and extract basically the top pavement surface temperature. So because when you look at the ICM output, it goes with depth. So there's tons and tons of different measurements. So once we matched the timestamps, things were looking a little bit better. We're looking at hourly temperature for basically 5-6 years. So I mean, that's a substantial amount of data, and to make sure that Excel doesn't crash or whichever software you're using was quite a challenge at times. We also removed any outlier temperatures, which we deemed as any temperature, any measured temperature that's plus or minus 50 degrees from the predicted temperature. So it's a fairly big range, but it really affects your model if you don't look at those or consider them or removing them. So that's what we ended up doing for this particular study. What we looked for at each different station is the measured versus predicted, and then we looked at the time series analysis. So that's the main comparison we're going to make here. All right. So now here's an example of one site. I'm pretty sure this one is an IDOT site. So you can see it's a fairly good prediction between the predicted and measured. This little area is a little strange. There's something in the ICM that we had to change and to make sure that gets corrected, and you'll see that later on. A pretty good R-squared of 0.97, and we saw this for most of the stations. Most of them had a very good comparison between the measured and predicted. So as you see here, we have the time series, the hourly. So it basically just looks like a big blob, but there's little dots in there that's basically an hourly point. And it fluctuates throughout the day, throughout the month, weeks, years. So one thing I want to draw your attention to is over here. So you see this is the residual, so this is measured minus predicted. And you can see it fluctuates for between the winter and summer months. So here you can see this is July 2012, and then in January 2013, the residual error is much, much less. So it helps to know that the model is very accurate at lower temperatures. And for this particular study, that's what we wanted. That's good. All right. Now, this is another site which did not give such good results. So the measured here is very, very high compared to the predicted, or very, very low. I mean, there's just a big difference between them, and very terrible R-squared for this particular site. And then we looked at the time series. You can see it's very obvious where the errors lie. So what we ended up doing for this particular site is the data after basically late 2011 up until the rest of 2015 looked pretty good. So what we ended up doing is we got rid of this, basically anything prior to late 2011, and used the rest to compare this particular site. I mean, there were maybe 6 or so sites that had something similar, but it was very apparent when that happened, so we were able to delete some of the data, but still make good comparison. If there were only a few temperatures for certain areas, we just got rid of the entire site, depending on what the issue was. All right, so the first thing, another thing we looked at was 2 different climate data sets. So the first one was the original climate data from Pavement ME, which is all at actual weather stations, so at airports, different areas. But it was last updated in 2013. So some of the issues with that is it's a single weather station. You might be miles and miles from your actual weather station or your actual site. So that's one limitation. Also, there was quite a few errors within this data set and inconsistent data records. So we moved to the North American Regional Reanalysis Climate Data Set, which is an assimilated climate data from weather stations. I mean, it takes into account many, many different data sources. So that was but it is a model, so there's not an actual physical station that measures this data. But it gives a pretty good coverage. It's about 19 by 19 mile grid, and it covers the entire North America, which is very useful for setting up a virtual station anywhere that you want, especially if you want to go look at historical hourly climate data. The data is reported every 3 hours, so to get an hourly, we use just an interpolation process. And a great thing about it is there's consistent data records from 1979 to present. So I mean, it's very, very well in depth, and that's 36 years for currently that we use for these data sets. And this past year, the hourly climate data in Pavement ME was updated to use the NAR climate data. So it's and what's very useful is you don't have to do any post-processing. There's no missing data. It's easy to use, and you're not going to repeat. Say if your site only has 5 years worth of data in the Pavement ME, it repeats every 5 years. So that's not going to happen anymore unless you go over greater than a 35-year design. When we compared these values, it's still very similar results. I mean, you see a pretty good prediction or comparison between the predicted and measured. This is not the same site as before, so it's a little bit different. More data, 19,000 data points. But the trend still is the same. You can see here there's a little bit less air at lower temperatures when it is winter. I think this is also an IDOT section. But overall, it was pretty similar between the NAR and the original, but the maximum R squared in a sense. I have a next slide I'll go into a little bit more detail, but for the rest of the analysis, we use NAR data just because it's consistent. We don't have to do any post-processing or worry about any missing data. As we saw, lower air for areas closer to 32 degrees, which is good for the purpose of this project and to verify the prediction capabilities of the EICM. As you can see here, we looked at the air for all temperatures. I mean, it's pretty low. We looked at plus or minus 10 degrees from freezing, and we looked at plus or minus 5 degrees from freezing. So I split it up by PCC, HMA, and composite because that's what we had for this study. So it's very within 2 degrees for basically anywhere close to freezing, which is pretty good from a climatic standpoint.
A couple quick questions.
Mm-hmm.
The predicted pavement temperatures you show, they're all surface temperatures?
Yes.
And the second one, the NAR data, is this still NOAA providing this? Or?
This was it's not NOAA. I can't remember the actual acronym for it because they change all the time. But it's definitely it's similar to, are you familiar with MERA? Like NASA came up with a assimilated data set, and it's similar to that, but it's not actual weather stations. But it's the very closest to the surface because I think it goes to like 37 or 38 different levels throughout the atmosphere. And we used the lowest one and got the temperature, wind speed.
And it's available public.
Yeah. You'll have to change a lot of things, or it's all just individual data sets. So what you want, there's some processing involved, but yeah, it's publicly available. And the next thing, the biggest difference between the original and the NAR data set is just the distribution of your R squared between all of our projects. So as you can see here, we have some projects with very minimal R squares, but once you get to the NAR, all of them are greater than 0.75. So that just helps and gives us more confidence in the NAR data set, and we're comfortable using forward, or using this going forward. All right, so the next part was to look at the model calibration. And how can we further improve upon the prediction capabilities of the EICM? So the main things we looked at were the surface shortwave absorptivity. We looked at the heat capacity and the thermal conductivity of the materials. And these values are different for, a little bit different for concrete and asphalt. So we didn't want to deviate too much. We didn't want, because the predictions were already pretty good, we wanted to make sure that we're within realistic values. So we switched from, so you can see the Pavement ME default values are right here. So it's the different PCC and HMA are a little bit different, and the same with for thermal conductivity. And we just moved it up and down by not much, just to see if there is a difference in predictions. Let's see. So basically for each of the sites, we had a matrix. For PCC, we ran, each one had 27 different combinations. We ran that, I think it was about 1,026 different runs for all of them. And then once we have that, then we go to the next step. But first I want to kind of show the differences between each one. So this is one particular project or site where we changed the absorptivity to 0.5, and 0.85 was the default, and then 1 is the upper limit that we specified for this example. These might not be necessarily realistic to a particular project, but it gives us an indication of what these values do. So the first one, we can see if we have lower absorptivity, we get lower pavement temperatures, predicted pavement temperatures, especially during the day. So this is between December 1st and December 2nd. So you can see it makes sense to see here, and then during the nighttime it's not as different. And then same, if you have higher absorptivity, you have higher temperatures. And then the next one, this was thermal conductivity. So it's very, you can barely see the difference in these. Some factors here, this might be different at warmer temperatures compared to what it is for colder climates or colder during the winter, but we didn't look at those, so they might significantly change when you look at when this data is changed. And then for heat capacity, it was pretty interesting. You can see lower heat capacity gave you higher temperatures during the day, but then lower temperatures during the night. For the most part, that's pretty much what you see throughout. And the same with the higher heat capacity gave you lower temperatures during the day and then higher temperatures at night, because how much is stored. So that's pretty interesting to see. So now we ran our different matrices, and the process of it was to basically you create a file for each one, run it, extract the data, and calculate the root mean squared error for each combination of pavement type. And it was about 1,026 different runs. And in order to kind of come up with one value for a particular pavement type, I looked at the top 10 RMSE combinations. So as you have your thermal conductivity, heat capacity, and absorptivity, I ranked them based on the plus and minus 5 degrees from freezing. And that way we use that to further refine our results. And once we have that, for all the different combinations and pavement types, we did a weighted average of the top 10 combinations for each site, and then we averaged, basically came up with a value that we can recommend for each pavement type. So this is kind of shows you a matrix of what it looks like. So we have, I think it's thermal conductivity. Yeah, green is thermal conductivity, white is your heat capacity, and your red is your absorptivity. So once we have these for, this is the, basically this one showed the lowest RMSE for site 1, site 2, site 3. Most of these combinations didn't vary significantly, but they did for some areas. So in the end, we came up with an average value. Thermal conductivity is 1.5, heat capacity of 0.3, and absorptivity, and this is 0.9. So this was for rigid pavements. And then for flexible pavements, it was a similar process. So we came up with 1.08, 0.25 for heat capacity, and 0.83 for absorptivity. So based on conclusions, we recommended for concrete materials to use a thermal conductivity value of 1.5, heat capacity of 0.3, and shortwave absorptivity. We actually kept that at the default values because there shouldn't be that big of an impact on absorptivity at lower temperatures. So we didn't want to make, since we didn't look at the higher temperatures, it might have a bigger impact for those. So we didn't want to, we kept all of these at default values. And then for asphalt material, we use a 1, 0.25, and then here you can see the MEPDG default value. So it's not very different, slightly, but that just depends. And then the root mean square summary for all these calibrated sites. I mean, you see 3.9, it's fairly consistent throughout. And then your mean error summary is much lower. I mean, it's less than a degree for most sites except for the composite tollway sections and the PCC sections. And overall, it was a very good, there was a very good comparison between the measured and predicted, especially at low temperatures. Calibration slightly improved the EICM, but overall the EICM was pretty good already. This can be used as a real-time pavement temperature prediction tool, and the virtual RWIS application will, I'll show that to you now. Okay. I don't know if it'll go over there, but. All right, this might be a little hard. Actually, I know what I'll do. Just give me a second here. All right. All right. So here you can see all the different stations that are available in Illinois. So I mean, you saw the few real RWIS stations, and then now we supplemented these with actual virtual stations. So if any of you watched the TRB webinar yesterday, Greg probably went through this. So I don't know if you have or not. So I mean, these are mostly along roadway on interstate freeways. I mean, we can set this up anywhere. As long as we have the pavement structured, it's not going to be an issue. So say for this particular, well, actually, let's do something around here. So we'll do the RAN tool site. And then we have, you can look at icing or you can look at freeze thaw. So if we want to look at icing, right now we've had pretty good weather, so it's not going to be iced or close to it. I think there's a potential, this is today. You can see the chart will give us the pavement temperature and the air temperature. Something on Saturday, there might be a few things, but it's not going to be any frost potential, especially since there's not going to rain too much. And then you can look at data tables if you want to look at the hour itself. Another aspect, so we can look at, I think January 2016 was pretty cold. Then you can see the historical records of it. And we'll go to a chart. And you can look at whichever days you want. So you can see here it's very cold temperatures, and you can see the pavement's pretty much frozen throughout. Not necessarily an ice event because it was so cold already. Okay, so that's the freezing part, or icing. And now we want to say, if we want to look at the freeze-thaw, so it gives you your thaw depth and then your freezing depth, which is not very much at all for the current data. So you see they're very close. I mean, once it gets to basically 0, I mean, that means that there's no thawing or freezing going on. If we go to January, let's look at April or something, actually. March. Okay. Not much going on there. Yeah, so here you can see you have a very deep frost depth, and your thaw depth is only going 3.6 feet or inches. And here, all of a sudden, there's probably a warm event where they match up. So there's no freezing or thawing going on. So one application for this is when road maintenance crews want to predict, well, for the icing part, when road maintenance wants to go out and salt the roads to get a very good, or to get ahead of it and really see when they have to allocate their resources. And then for the freezing and thawing, you can definitely use it for especially spring load restrictions. That's one application for it. So that could be very useful. And with that, I don't know if you wanted to see more, but I think with that, I want to thank you for stopping by today, and let me just make this bigger. And I want to just acknowledge the members of the technical review panel for this project, the Illinois Center of Transportation, and Illinois Department of Transportation, FHWA, Illinois Tollway, and McHenry County, because we wouldn't be able to get all this data if it weren't for all the collaboration we had with them. All right, thanks. Any questions?
Earlier, I think it was with the original data set, you talked about eliminating data points that were more than 50 degrees Fahrenheit above. I was wondering how you arrived at that number, and if you had tried any other values and saw what kind of R square value you got.
It was kind of just arbitrary. We just selected that, and we didn't see many. We thought that was probably the most realistic. We didn't want to go to too much higher or lower. We could, but we didn't at that point.
I mean, the thought that occurred to me is that there was 40 degrees higher than your prediction, might that not actually be the lowest? You're still getting.
Yeah, we still got pretty good. It's just those values that are very much higher or much lower than the predicted. I mean, for everything else, it was pretty close anyways.
I have a couple of things.
The first is the data, the raw data publicly available.
For
The temperature data.
for what, the measured or predicted?
Yeah, measured.
I don't think it is. I'm not 100% sure because that's from it might be. It depends on what the state does with their RWIS data. I'm not sure. I mean, I'll have to ask.
Is the software publicly available?
No.
No. But
This is a commercial product, but if you have the EICM, you can basically get your predicted data. If you run Pavement ME, it's embedded in Pavement ME.
Third and fourth questions are going to be about the coefficient of conductivity and other input parameters. So you kind of back calculated them to minimize your error in EICM, like the prediction model.
Yeah.
So do you, for example, let's say I am designing a pavement in different state than Illinois. Would you still recommend to use the same, like the values that you are recommending in the presentation?
Probably not. I mean, it could be different, it could be the same. I mean, I think that calibration aspect is site dependent and state dependent. But we did it for Illinois and it just worked out. But you can change those values. But you also, the physical property of it, you can either measure it or not. We didn't. But you want to make sure that you don't go beyond the limits of the material. I mean, that's because concrete's only going to have a heat capacity of a certain range. So that's why we didn't want to go. First, we actually ran it where we went to the limits of the actual values, and that was unrealistic. I mean, that's why we went back to a smaller limit. But it could be different for different states.
Well, one thing to answer that question, if you go back to the 1997 study, Greg Larson worked with Professor Dempsey for Minnesota in that report. They have done a complete, actually, sensitivity study of all the inputs going into EICM. So that was the thing where you will find something.
Yeah, and the default values are pretty good. I mean, that over the years it's been tested and looked at, and the default values will probably be okay for most situations.
How realistic is to assume that it is constant throughout the years, like it's not changing, because you saw the data for a couple of years, and we assume the same coefficients for the entire time span. So how realistic is that assumption? Change.
Especially absorptivity is going to change much more, especially at higher temperatures. And that's why you see all the higher air at higher temperatures. But for us, we didn't need to look at that. So for the virtual RWIS application, that was enough for us to just modify those values in that aspect. I mean, they didn't change much.
Like implement the use of the software, because for example I will be using this software like 2 years from now on, and I will be still using the same inputs coming from like the same section. So like, do you think that this can affect the accuracy of the prediction?
I don't think so.
So
it was pretty established.
We had a question online. In the last couple of years, there's been research showing improvements to thermal modeling, boundary conditions, and convection, for example. Does EICM incorporate these?
I am not 100% sure, because Greg's the expert on this, and I've just hit the surface. I mean, Dinesh, do you know?
I don't think we have made any changes to temperature models.
Yeah, EICM's been pretty constant.
One thing is a follow-up question to that, actually related to your last slides, maybe, where you're showing the freezing and the thawing fronts and things for the same day, like, different contours.
These ones?
Well, I can't see them.
Sorry.
No, this is towards the end.
Oh. Actually, I'm just gonna not duplicate the displays here. 1 second.
The frost depth and the thaw depth, I guess.
Okay.
Those ones.
Yeah, I just want to change this here real quick. That way I don't have to.
Yeah, some of those predictions come from the Corel's original modified Bergen, whatever equations, right? For the first step penetration.
Yeah, whichever.
For
You see these ones?
no, you go to the end of your presentation, like the second last or so, where you were showing the depth.
We just had these.
Oh, maybe it was in the demo.
Oh, okay.
Right.
I can go back to the demo, yeah. So right now, the chart won't.
Right, those, for
This.
example. I mean, the big thing about the soils, aggregate materials, base course, subbase, whatever, or stabilized bases now, or stabilized soils like lime stabilized or cement. Durability aspects are very important, right? The number of freeze-thaw cycles and things.
Yep.
Is there a way to maybe use these features to be able to predict in any local area the number of freeze-thaw cycles at any depth, the pavement, different pavement layers will experience over the years? Because that's a key for our durability studies.
Yeah. I mean, I know once you characterize, in the ICM, you can do based on the material properties of each layer. So maybe just not look at just the surface. I mean, this goes to deeper. I think I'll have to ask Greg, but I think it might be possible.
Because more and more we're going into sustainable
Mm-hmm.
uses of different kind of, byproduct or recycled materials,
Yeah.
reclaimed and used as layers. Their durability aspects become an issue, and all of that is related to the number of freeze-thaw cycles.
I'll ask.
That's something for you guys to think about as the next step for this software.
Yeah, this will be
You
recorded.
can
so-
mention that to Bill Maverick or Greg Larson.
All right. Yep.
This question occurred to me when you were showing the data, and it's not something that comes directly from your software, but if you could glean it from the data. Is there a pavement section that's most susceptible to icing? Probably a lot of people already know that. I just didn't, and it occurred to me you could compare different sections and profiles and see in there which one predicts icing and which doesn't. So, is it an HMA, is it PCC, and does the underlying layers factor in very heavily at all?
To a certain extent, but I took that out, but there wasn't a big difference between I controlled for that and then didn't see a big difference between pavement type. I mean, temperature-wise, it was pretty similar. But it just depends on where your water table is, what freezes, where everything is. I mean, comes down to construction too.
All the calibration outcome has been put in the Pavement ME already.
This? From the calibration? No, this is just for virtual Arwis Illinois sites. So this isn't part of Pavement ME or global calibration or anything.
So if we are using that Pavement ME, that if we want to look at a pavement here, then we have to select a weather station, which is the closest to here, right?
Oh, you mean the weather data?
Yeah.
The weather data is updated, but right now it's only, so there was 1,083 original climate stations, and now there's also 1,083, but they're updated with just with the NAR data set. So you're still selecting the closest station. But what you can do, there's a Merit Climate tool where you can basically come out with your HCD files for anywhere in the world. But you are going to get different predictions because it is a different data set. That way it's a bigger grid. It's I think 20 by 30 miles or something. But if you want to get to the NAR data, you can get it for anywhere in North America. It's just you'll have to kind of do it yourself.
So our local agencies going to be able to use this in the state for predicting icing and maintenance?
I mean, we hope so. I think so. As long as we have the pavement structure, we can set it up for anywhere because we have the NAR data to look at past, and then we use Weather Underground for forecasting.
All right, any other questions? Well, in that case, we'd like to thank you,
All right.
Dr. Brink, very much.